A short while ago, we posted a video on the IRR and how to tune the IRR. We had a lot of responses, most of them positive, thank God, and a lot of followers are also questioning about could we talk a little bit more about KPIs and especially the IRR, since the IRR is used in the most of the investment proposals. So in this video, we briefly are going to give you some more depth into the calculation of the IRR. Up to you, De Jong.
Thanks. So what is the IRR? Well, before we talk about the IRR, we first need to talk about the net present value, which is abbreviated by NPV. And this is defined as the time-weighted sum of all cash flows where we take into account rent or the rate of return. So we conveniently write this as these are the cash flows, the C, and we compound the interest, the rate of return, using this formula. And okay, this is a nice formula, but how does it look? So let me try to draw that over here. So suppose we have the NPV over here and the rate of return over here. Then it usually looks something like this. And there are two interesting points already in this graph. So the first point is over here, which is where the rate of return is actually 0. So what is this point? Well, it's precisely if we fill in a 0 here, then we just get 1 to the power ti, which is 1. So we just get the sum of all cash flows. And this makes sense if we think about it, because when the rate of return, when the rent is 0, then the net present value indeed is just the sum of all your cash flows. So when the sum is larger than 0, then you have a positive net present value. And when it is smaller than 0, of course, your net present value is also negative. So that's one interesting point. So this is just the sum of all cash flows. Of all. But a more interesting point is actually the point where the net present value is 0. So what is happening over here? Well, it means that basically at this rate of return, which turns out to be the internal rate of return, the sum of all your cash flows which are weighted with the rate of return as based on the timing at which these cash flows occurs is actually 0. This means that if the rate of return would be higher than the internal rate of return, so this point here is the internal rate of return. So as the rate of return would actually be higher, so the banks would have a higher rent, for example, that would actually mean that your net present value is negative, because then we end up in here. And vice versa, if the rate of return would be lower than the internal rate of return, then the net present value would be positive. So in a short summary of what I'm saying basically is that a high internal rate of return means that your investment proposal or portfolio is very favorable. So how is the internal rate of return actually computed? Well, for that I first need to erase my board, and I'll be back in a second. So let's delve a bit more deep into the net present value and the internal rate of return. So one way to look at the net present value is like a bank account where you have compound interest and you're trying to compute what is the value of your bank account. But a mathematician actually looks at a net present value as a polynomial. So before I tell you what a polynomial is, let me first show you the trick that mathematicians use to make it into a polynomial. So we define a variable x, which is equal to 1 over 1 plus the rate of return. And then we can write the NPV as a function of x, which is just equal to the sum over all these cash flows times x to the power ti. And this expression is the general expression of a polynomial. And polynomials have been studied by mathematicians for ages. So the ancient Greeks and the Arabics, they were already interested in these things because they want to know what kind of value for x we can choose so that this polynomial is equal to 0. So what is x? And a very simple polynomial is a polynomial of the second degree. And this is also known as a parabola. And when we, for example, look at a parabola, it looks like this. And this is the polynomial, for example, y is x squared minus 1 or something. So here is the minus 1. And these have 2 points where y, the polynomial, is 0. And the nice thing is that we have a general expression for any second degree polynomial what the zero is. So some of you might recall it's the ABC formula. So when we have ax squared plus bx plus c, this is the general form of a second order degree polynomial. This is equal to 0. Then we have two options for x. We have computed this, which should be something like minus b plus or minus. So these are the two possible values. And then we get a b squared minus 4ac over 2a. I guess you all remember this vaguely from high school, but this is a very nice result. The problem is that when your polynomial is of a higher order degree, these formulas can become very complex, for example on the third, the fourth or fifth order degree, but above that we cannot find a solution. There are actually mathematical proofs that some of these polynomials cannot have such an analytic solution as this. And that's why we have to rely on numerical methods to determine the internal rate of return. So even when you do in Excel the computation of an internal rate of return, it's actually a numerical approximation of the real thing. So that's what makes the internal rate of return complex. But in the end, it's just the root, which is the 0 point of a polynomial. So the computation of the internal rate of return boils down to finding the root of a polynomial, which cannot always be done analytically and has often to be done numerically. Fortunately, we have computer programs that can do it for us, and we are just interested in the results. But it's still nice to understand how this IRR actually depends on the net present value. So to make things a bit more concrete, I have made up a toy model with two portfolios, a target and a measurement, and 4 cash flows, and only the rent and the vacancy differ between the portfolios. And if we look at the internal rate of return, we see there is a slight difference. The measurement is outperforming the target portfolio. And we want to see now how does this translate to this scenario with polynomials, and how does the net present value actually change. So what I will plot here is actually the net present value as a function of the rate of return again. And now in first instance we look at the target portfolio. So this is where the value is 0. And the target portfolio will look something like this. So this is the NPV curve. And now the rate of return at which the NPV is 0 lies somewhere over here, which should be the 17.69%. Now what happens when we increase the rent from 80 to 100? Then, as we would expect, the net present value would also just raise. And this means that actually this curve, this entire curve, would just become higher. So it would look something like this. And now what you see immediately is that the point where the net present value actually is 0 is shifted to the right, so from here to here. Which means that the internal rate of return actually gets higher when the rent gets higher. Similarly, if the vacancy would get worse from -10 to -20, then the curve would shift down a bit, and so we would end up with some net present value curve looking something like this. And this is precisely the internal rate of return of our measurement portfolio. Now, the difference between these is again this 1.18%. And the nice thing about this understanding is that now we can intuitively and insightfully see what happens when components of our portfolio change and how it changes the internal rate of return. Now, because this is so insightful, at Funstar we have developed algorithms to make this concrete, to determine exactly what is the effect of, for example, an ESG investment on your internal rate of return. And this insight is then used to generate very powerful and insightful data visualizations.
Do you want to learn more about this topic? Please download now our white paper by clicking the link below.